Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome again to Mewa Digital Hub channel. And just like usual, today is a chemistry lesson in which this chemistry lesson is very unique. We're going to study this paper, which is a paper 1 of Maranda High School. And many people think that this paper is usually hard, but it's not that hard. It's very easy and very easy. So just likewise, don't forget to subscribe to the channel, click on the notification bell, and let's start the session just like usual. Now, for the first question is asking or is illustrating a diagram, and the diagram below shows the process used in mining sulfur. Study it and use it to answer the questions that follow. Now, these are 3 pipes. Okay, this one is usually the innermost pipe, and we have the outermost pipe, which is the C1. Usually it's big. Okay, the outermost pipe is usually big, and then we have the middle pipe, and each of these pipes have their own processes, okay, and own functions. So for this these 3 pipes are used in mining sulfur. What does mining sulfur mean? They used to extract sulfur deposits underground. Okay, they used to extract sulfur deep underground. So this process, we call this process as Frasch process. Frasch came from a person who discovered this. Okay, it's called Frasch. And I don't know why he's called that. Just ask him when you find him. Okay, but for now I think he's dead. Okay, so we have 3 pipes: the middle pipe, the innermost pipe, the outermost pipe. So we have deposits here. Now the deposits are usually in solid form. And how do you remove that solid sulfur outside from the underground to the ground itself, or to the earth surface? So how do you get it? So these pipes are usually working. So each of these pipes will help the sulfur to come out from that underground place. So each of the pipes each of them have their own functions. So let's start with the outermost pipe. That's the first thing which you need to know. First of all, the outermost pipe, usually superheated water passes through the outermost pipe. So the superheated water, when it reaches the solid sulfur, it melts the solid sulfur. So it makes it in form of molten form. So the function maybe of this outermost pipe is just to pass superheated water at 100 degrees, at 170 degrees Celsius, and also 10 atmospheres, so that you can melt the sulfur deposits into molten. And the next pipe is the middle pipe. Now the function of the middle pipe is just to pass compressed air, so that it can force the molten sulfur and into the innermost pipe. So it just acts as a pump. So it pumps it out. So once it's pumped here, so it comes here and pumps the molten so that it can pass through the innermost pipe. And that comes to the function of the innermost pipe, and that is to make sure that the molten sulfur and the water passes through the innermost pipe. So hopefully you've understood that. Now question A, name the process illustrated above. So we call this process Frasch process. Give the function of pipe B, and pipe B is the middle pipe. Okay, pipe B is the middle pipe, and its function is just to remove both a mixture of molten sulfur and water. So that's the only function. Okay, for the other one, which is C, and C is your outermost pipe, and we've said the outermost pipe is used to pass or to allow passage of superheated water at 170 degrees Celsius and 10 atmosphere pressure and 10 atmospheric pressure. So hope that is understandable. Now for this, the other question, name 2 crystalline allotropes of sulfur. We have 2 main common ones. One is called rhombic sulfur, from the rhombic structure, and the other one is called monoclinic sulfur. We also have allotropes of carbon, and we have many. We have diamond, we have graphite, we have other allotropes. Some are synthetic and some are natural. Now for question 2. Question 2, the atomic number of nitrogen and fluorine are 7 and 9 respectively. Draw using electron dots and cross diagram to illustrate bonding in the molecules of nitrogen. Now let's write the electronic configuration of nitrogen. Now nitrogen, when you look at the periodic table, you'll find that nitrogen is at the 7th position. So it should be written as 2,5. So 2,5, so it has 5 electrons in the outermost energy level. So it means that for it to gain stability, it needs 3 pairs. Remember, I'm saying 3 pairs of electrons, because this nitrogen usually bonds with its other nitrogen atom with the help of weak van der Waals forces of attraction, also covalent bonds. So we covalently bond it. So, and you know that covalent bonds just require sharing of electrons. So that's the reason why I'm writing 3 pairs and not 3 electrons. Okay, because the other nitrogen will also require 3 pairs. So remember, nitrogen is a molecule. So nitrogen is written like this. So let's draw the nitrogen structure, which is this. I will just draw the outermost energy level. So this is nitrogen and this is nitrogen. And we said that it requires 3 pairs of electrons. So now if you subtract 3, you remain with 2 electrons outside. So that's the first pair, the X and the dot, the second pair X and dot, and the third pair X and dot. And remember, you remain with only 2 electrons. So you remain with 2 electrons here and remain with 2 electrons here. Or you can opt to write it here. Let me just write it here. So here and here. So that is the bonding. Now remember, you don't need to use a divider to draw. So you just draw it using your hand. The fluorine now, the fluorine molecule, which is F2. Remember that fluorine's electronic arrangement is written as 2, 7. Hey, listen, BBC. Yeah, it's written as 2, 7. So it requires only 1 pair of electron. So let's draw fluorine. So fluorine is also a molecule. So which is written like, which is drawn like this. So requires only 1 pair of electron. Okay. So if you subtract 1 from 7, you remain with 6. So it just remains 6 electrons in the outermost energy levels. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Khalas. Let's go to the other question. Question B, with reference to the diagram in A, state why fluorine is more reactive than nitrogen. Remember that nitrogen had 3 pairs, right? So it had 3 bonds. So it has 3 bonds in its structure, while fluorine, let me write it up. Nitrogen has 3 bonds and fluorine has double bond. So nitrogen having a triple bond is usually more it requires more energy to break those triple bonds than the one with the 2 bonds. So if it requires more energy to break those bonds, it means that its reactivity will be quite slow, because for it to gain electrons, you need to break those triple bonds. And for this, since there's an easiness of breaking these bonds, it means that it can gain electron quite easily. And remember that the activity is all about losing or gaining, the easiness of losing or gaining electrons. So the easier it loses or gains electron, the more reactive it is. So for this case, fluorine is more reactive, is because there's an easiness of gaining electrons, since the bonds can be broken easily than the nitrogen one. So with reference to the diagram, so I'll say that nitrogen has triple bonds, while fluorine has a single bond. So you don't leave it like that. You also explain what happens, but you can also say single bond is usually weaker. Single bond is weaker than triple bonds. Is it single bond or double bond? I think it's a single bond, sorry. I forgot. I thought it was so for the fluorine molecule, it has a single bond and not a double bond. So single bond is weaker than triple bond, and hence easy to break. So hopefully that is understandable. So let's go to question 3. Complete table below table 1 by writing the formula of all the products formed when the metal nitrates are heated strongly. For the case of now nitrates, they're in 3 stages. For the first stage, which is potassium nitrate and also sodium nitrate, if you heat potassium nitrate or sodium nitrate, you'll get potassium nitrite plus nitrogen for oxide. So for this case, you'll get potassium nitrite, which is written as potassium nitrite. Okay, KNO2. Remember that NO2 has a valency of, or has a charge of -1, while the potassium has a charge of +1. So the 1 will take the 1 and gives you KNO2 plus nitrogen for oxide. Remember, you're writing the formula and not the word equation. So it should be in chemical in terms of symbols. The other one is lead to nitrate. Now, if you heat lead to nitrate, it doesn't give you lead nitrite, but instead it gives you lead oxide. And remember that lead has a valency of 2. Oxygen also has a valency. When they interchange, they just give you lead oxide like this. We discourage students to write something like this. It's better to write it this way: lead oxygen, then you have lead 2 plus and oxygen 2 minus, and therefore you get lead O. So you get lead oxide plus nitrogen for oxide plus oxygen. So you don't need to balance anything here. So for the case of silver nitrate, that the third case, instead of getting silver oxide, you'll get silver only. So you get silver plus nitrogen for oxide plus oxygen. Just imagine your lab has silver nitrate. So every time you heat silver nitrate, you get silver. And just so in the case you heat gold nitrates, you get gold. But that's why you don't usually have those types of nitrates, silver nitrate or gold nitrate. Unless you're studying Strathmore University, that's a different case. So question 4, the molecular formula of hydrocarbon is C4H6. So give the general formula of the homologous series to which the hydrocarbons belong. Now this one, it can't be butane, but instead is butane. And the homologous, the formula of the homologous series is CnH2. H2N minus 2. Even if you look at it, is C4, right? So H is obtained through taking by taking 4 times 2, then minusing by 2. So 4 times 2 gives you 8, and minus 2 gives you 6. So C4H6. This is the homologous series for alkynes. Okay, now it's better to know the homologous series of alkane, alkene. The homologous series of alkane is CnH2n plus 2. That's for alkane. We have alkene, which is CnH2n only. We have alkyne, okay, which is Cn now, H2n minus 2. We also have alkanols, which is CnH2n plus 1, which is an ethyl. Then you put just the OH. This is alkanol, or also referred to as alcohols. Okay. We also have alkyls, but for the main ones, the hydrocarbons that you need to study is the alkane, the alkene, and the alkyne. So now, for the other question, is asking you to draw the structures of 2 positional isomers. Remember, this is not structural isomers, but instead is positional isomers. So whatever you'll change is just the bonding, the triple bond. So the position of the triple bond. So remember that this is an alkyne, and this C4H6 is butyne. So let's draw 4. So 1, 2, 3, 4. And let's put the triple bond, because since it's an alkyne, it has a triple bond. So we'll put the triple bond here. And since there's 1, 2, 3, so it should give you 3 here. And then 1, 2, 3, 4. This one doesn't require any hydrogen attached to it. This one requires, and this one requires. So that's the first positional isomer. Let's draw another one. We just put this to the other side. So let's draw another one. So C, 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 C. And we put the triple bond in the second carbon chain, which is here. So here will be 3 hydrogens. For this case, we can't put hydrogen. For this case, we also can't put hydrogen. So let's put hydrogen last position. Now, how do you name this? Okay, how do you name this? For the first one, we start from here, because that's the simplest way. You can't start from here, because it gives you the longest carbon chain, and it's very hectic. So we start from here. So it's 1. So we call it but 1 ine. Okay, 1 because of the position of the triple bond. For the other one, the triple bond is located at the second carbon chain, and therefore we write it as but 2 ine. So that's the answer. Okay. Now, question 5. The graph below shows how the solubility of oxygen varies with changes in temperature. So how the solubility of oxygen varies with changes in temperature. So if you look at the curve, solubility decreases with increase in temperature in a sugar. If you increase the temperature, the solubility of that oxygen gas decreases. So the more heat you apply, it means that less oxygen molecules will dissolve in water. So that's the meaning of it. So question A, explain using kinetic theory why the solubility varies as shown. So you'll say that solubility of oxygen decreases with increase in temperature. Even if you don't know the other explanation, this gives you 1 mark. With increase in temperature. Okay, with increase in temperature results, why does it do that is because the particles gain kinetic energy. So once they gain kinetic energy, they don't dissolve inside that water molecule. So they gain kinetic energy and escape from the solution. So hopefully that answers the question. Now let's continue. Question B, explain why the pollution effect that may be caused by a large increase in temperature of seawater. Now we say that increase in temperature reduces the solubility of oxygen inside water. So if oxygen doesn't dissolve in water, it's at the end of the day, that oxygen that is used by fish to breathe won't be used again because there's no oxygen dissolved in water. So as a result, the fish will die. So remember, the less dissolved oxygen in seawater, less dissolved oxygen in seawater will lead to suffocation, or will lead to the death of marine life. Okay, organism, whichever you can say. You lead to the death of marine life due to suffocation. Because there's no oxygen, then how can they breathe in? Now, let's go to the other question, question 6, which is empirical formula question. The percentage composition by mass of an oxide of iron is 70% and 30% oxygen. So determine its empirical formula. For now, we'll use percentage mass, or let's use mass, and regard mass as the percentage. So this is 70, this is 30. But let's first write iron here, and let's write oxygen as well. So let me just a bit, I don't know why the PDF is going this way and that way. So let me write it here. So the mass is for iron is 70%. They didn't give us the actual mass, so you'll use the percentage. So this one is 30%. Now we have something called the molar mass. Okay, and the molar mass for iron is given is 56, and for oxygen is 60. Now we search for something called moles. Now we have the structure here where this is mass, and this is moles, and this is molar mass. Now for you to get moles, you take mass divided by molar mass. So therefore you take 70 divided by 56. So how much do you get? If you take 70 divided by 56, ignore the 100%, so you get 1.25. So moles is given by 70 divided by 56, which gives you 1.25. For the other one is 30 divided by 16, which is mass over molar mass. So 30 divided by 16 will give us 1.875. Now after that, we search for something called mole ratio. And how do you get mole ratio? You divide out of the 1.25 and the 1.875, you divide by the lowest, and the lowest is 1.25. So you divide 1 by 1.25, also divide by 1.25, and therefore, okay, and therefore, let me just write it here so that you can see it. So let me just write it here. Remember 1.25, and this is 1.875. So you divide by 1.25 and divide by 1.25. This one will give you 1, but for this case, it gives you 1.5. So if you take 1.875 divided by 1.25, it gives us 1.5. Now this is 1.5 and this is 1. Now you can't have mole ratio in terms of decimals. That's why you need to have it in whole numbers. Now how do you change 1.5 into whole number? Remember, if you round it up, you'll affect this one. So to get your final answer, it means that you need to multiply 2 here to give you 3. And on the left side, you also need to multiply by 2 to give you 2. So the mole ratio is 2:3. It means that iron 2 and oxygen are 3. So we have 3 oxygen atoms and 2 iron atoms, and that's your resultant answer. Question 7. Filtration is carried out in apparatus shown below. So this is filtration. Now we have something called filter funnel, which is this. This is the filter funnel, in case you don't know. Now, what is the process of filtration? Filtration is used to separate one insoluble substance, I think, most of the time. One that dissolves and the other one that does not dissolve in a solvent. So mostly used to separate those two. For example, we have sand and water. So one dissolves in a solvent and the other one doesn't dissolve. So for you to separate those two types, you just use filtration. But for the case of sand and water, we have water. So we just separate insoluble substances, which are the substances that don't dissolve in water. We separate them using filtration. We also have sand and salts. Okay, one dissolves in water and the other one does not dissolve in water. So now when it undergoes filtration, we have something called the residue and the filtrate. The residue is the one that remains on the filter paper, and this is the filter paper. Okay, the filter paper, and this is the residue. Since it doesn't dissolve, it won't pass through the filter paper, it will just remain there. And the one that passes through the filter paper and enters the beaker, we call that substance to be filtrate. So for the case where you want to separate sand and maybe salt solution, so when you mix those two in water, the sand will become the residue and the salt solution will become the filtrate. So question A, name X. Our X is residue. And now state one property that makes it possible to separate mixtures using filtration. And what's the specific property? The specific property is insolubility of substances. So insolubility of a solid in a solvent. Okay, of solid or substance in a solvent. So if you find a substance that doesn't dissolve inside a solvent, you usually separate it using filtration. Now we have again organic chemistry. Question 8. Table 2 shows the boiling point of ethane, butane, and ethanol. So this is ethane, this is the butane, and this is ethanol. Okay, now let's continue. Giving reasons for the following. Question A. Boiling point of butane is higher than that of ethane. Okay, boiling point of butane is higher than that of ethane. All of them belong to alkanes, but why is it that boiling point of ethane is higher than that of butane? And the answer is very easy. And the reason is, the boiling point of butane is higher than that of ethane. The reason is, butane has a higher mass. Okay, butane has a higher molecular mass. If you want to write higher mass, it depends with you, but it has a higher mass than ethane. So what does this mean? It means that butane will therefore have stronger weak van der Waals forces than ethane, and that's why it's very hard to break butane than ethane. Okay, hopefully that is understandable. The reason, so if you find some substance having a stronger weak van der Waals than the other, it means that you need a lot of heat energy to break those bonds. Now, for the other question, is saying a boiling point, why the boiling point of ethanol is higher than that of butane, and it's also a very simple question. The reason why the boiling point of ethanol is higher than that of butane is because ethanol has hydrogen bonds. So ethanol has hydrogen bonds. I'm writing higher. I don't know why. Ethanol has hydrogen bonds. Again, ethanol has hydrogen bonds. And hydrogen bonds are usually stronger than weak van der Waals forces. Are stronger than weak van der Waals forces. So as a result, ethanol will have higher melting point. Okay, ethanol will have higher melting point. So the hydrogen bonds are stronger than van der Waals forces that are in butane. So simple. So if the hydrogen bonds are stronger, this means that you need a lot of heat energy to break those bonds. Okay, with that, let's stop it at there. In the part 2 of this video, we'll try to finish the paper. So don't forget to subscribe, and it will be very soon that I'll post the other part of the paper also, so don't miss out the session as well. Assalamu alaikum wa rahmatullahi wa barakatuh.